We are continuing season 2 of integration practice. We are doing problems from the Stewart Calculus Early Transcendental textbook, 7th edition, section 7.5. We left off on number 7, so let's do a few more problems in this video. Okay, so we have this integral from -1 to 1, e to the arctan y over 1 plus y squared dy. Hopefully you can see a very obvious substitution, because u can be arctan y. Du is, what's the derivative of arctan? It's 1 over 1 plus y squared dy. And we get exactly that there. So let's worry about limits of integration afterward. As always, at least for me, I always just plug in first, substitute first, and then worry about the limits. So it's e to the u, and then this is just du. Hopefully you can see that, because here, e to the u, this whole guy, the remainder is exactly du. Limits of integration, when y is -1, we plug into there. U is arctangent of -1, which is negative pi over 4. When y is 1, u is arctangent of 1, which is pi over 4. So this is just e to u, evaluate from negative pi over 4 to pi over 4. That is just e to the pi over 4 minus e to the negative pi over 4. Okay. One other trick before I move on to the next problem, when we have limits that go from negative a to a, for example, here's -1 to 1, it's a good idea to check if it's an even or odd function. Hopefully you remember that. If it's an odd function, then the integral is 0. If it's an even function, we can put like 2 times integral from 0 to a. And usually when the limit's at 0, it's usually easier to calculate in fundamental theorem calculus. In this case, this function is neither odd nor even, so it didn't help. Okay, because otherwise this would have been like 2e to the pi over 4, something like that. But clearly it wasn't. That was neither even nor odd. It's because of this e to the arctan y. Arctan y is odd, but e is neither even nor odd, so that's why I made it neither. Okay, so that's a side note. Number 8, integral t sine t cosine t dt. So here I see a product of things, so likely we should use integration by parts. And before that, remember there's an identity that looks very similar to here. You know that sine of 2t is 2 sine t cosine t. So if I move this 2 to this side, this will simplify things actually. So we get half integral t sine of 2t dt. So instead of 3 terms, now I have 2 terms and a constant, which I can move the constant at. Okay? So here is the classic integration by parts. Okay? So I'll do it the tabular method for those of you that might not have seen it. We choose u and dv exactly the same as before. U would be t, because we want to reduce that power. And then over here is sine 2t. We differentiate u until we get to 0. Here we integrate just as many times. So it'll be half, negative half, cosine of 2t. Here would be -4th sine of 2t. Okay, and then we go diagonal, and then we also add a sign. We're starting from plus, and we alternate. Okay, so we multiply all of them together, and then add each diagonal, basically. Okay, so here we would get, so don't forget this half over here, half times, now we go over here, minus half t cosine of 2t, and then here would become plus 1/4 sine of 2t plus c, and this should be your answer. Okay, number 9. Integral from 1 to 3, r to the 4th, ln r dr. How do you solve this guy? Here, when we have an integral of ln, if you remember, hopefully you've seen this in lecture or something like that, we use integration by parts. And here, the other clue is we have a product of 2 things. Likely, we can use integration by parts to help us out. Okay, so let me do it the classic way. U and dv, we have to choose that. We have to let u be ln of r, and dv would be r to the 4th dr. Because if I put dv as ln r, how do we get v? We have to integrate of integrate the natural log. I don't know if you remember it, but you have to use integration by parts to find that in itself. So let's let u be ln r because we know the derivative of that. That's easy. 1 over r dr. dv is r to the 4th dr. So v, we know how to integrate that. That's 1/5 r to the 5th. Okay, so uv minus integral v du. Let's do that. 1/5 r to the 5th ln r. We evaluate this from 1 to 3 minus integral from 1 to 3 of v du. So we have a 5th here, and then r to the 5th divided by r is r to the 4th. This is easy to integrate. That's just power. So this I'm not touching. So usually I evaluate everything at the end together. Okay, so now let's do fundamental theorem calculus. By the way, we can simplify this to 1 over 25. Okay, plug in 3 first, so it'll be 3 to the 5th over 5 ln of 3 minus 1 over 25, 3 to the 5th, minus parentheses, we plug in 1. Well, when we plug in 1, log of 1 is 0, so everything there would go away, and then we get minus 1 over 25. Okay, and this should be your answer. Again, you can double check, especially this is a definite integral, you can easily check with a calculator. Okay. And actually, no, it's only 6 minutes in. I'm moving quickly in this video. Okay. So number 10, integral from 0 to 4 of x minus 1 over x squared minus 4x minus 5. Okay. I see this is a rational function, so maybe let's do partial fraction decomposition. So let's factor the bottom. That's what we get when we factor. So we can rewrite x minus 1 over x minus 5 times x plus 1 as a over x minus 5 plus b over x plus 1. Okay, so multiply both sides by the denominator. We get x minus 1 is equal to a x plus 1 plus b x minus 5. For here, I like to use it because there's only linear factors. I like to use the technique where we just plug in easy numbers like x is -1. Because this would go away, we get -2 is -6b, so b is a third. We plug in x is 5. Why do we do that? This would go away. We get 4 is equal to 6a. A is 2/3. Okay, so we can rewrite this as integral from 0 to 4. A is 2/3, so let me shift this back up. 2/3 times 1 over x minus 5. And then the next one was b was a third, right? So a third times 1 over x plus 1 all by dx. These are easy to integrate. They're just logs. Evaluate from 0 to 4. Now let's just do fundamental theorem calculus. It'll be 2/3 log of 4 minus 5, which is -1. Absolute value would be 1, plus a third log of 5, minus parentheses 2/3 log of 0 minus 5, absolute value. That would be log of 5, plus a third log of 1. Okay, the log ones would be 0. So we get a third log 5 minus 2/3 log 5. So that's minus a third log 5. I believe that's the answer. So you can, once again, double check. Okay, the next problem looks very similar, and I'll probably call it apart after this one. X minus 1 over x squared minus 4x plus 5 dx. Okay, so instead of a minus, we have a plus. So it looks very similar, but this plus makes the bottom not factorable. Okay, so we cannot do partial fraction decomposition because we can't factor the bottom. So what do we do here? So let's go down a list again maybe. Can we substitute? If u is x squared minus 4x plus 5, du would be 2x minus 4 dx. Doesn't quite look like that even if we factor out the 2. It'll be 2 times x minus 2 not that. So probably not substitution, at least that substitution. Integration by parts is probably going to be complicated. So because still this guy's not factorable if we put this as dv or something like that. So probably not that. Non-trig integral. Trig sub is not something squared plus something squared over here. Maybe we can force it to be like that by completing the square, but let's hold off on that. We might have to do that. And as I said, maybe not partial fraction decomposition as of now, but maybe again we can force it if we complete the square. Remember that technique? So actually let's complete the square now. So how do we do that? For this quadratic term to complete the square, we take the term in front of the x, so minus 4, divide by 2, and we square it. So that is equal to 4. Okay, because it'll be negative 2 squared, which is 4. So let's rewrite this as x minus 1 over x squared minus 4x. We want this term plus 4, but to make it equal, because we can't just say this, these are not equal. So to make it equal, it was originally a plus 5, so we need 4 plus 1. So let's write it like this. Okay, now after we do that, this becomes a perfect square. That's why we complete the square. It'll be x minus 2 squared plus 1. Okay, now this is better. Hopefully we can do a substitution. I forgot to dx. U is x minus 2. du is dx. As simple as that. Okay, so when we substitute, well, we have x minus 1 here. How do we get x minus 1 from our definition here? That's just u plus 1. Okay, now this I is just u squared, and then we still have the plus 1. Dx is just du. Whoops, du. Okay, is this better? It actually is, because now we can separate this into two integrals actually and evaluate them one by one. Okay, this you should recognize arctangent. This is just substitution. It will become a log. So it'll be, if you want to substitute, we already have u. So let's say v is u squared plus 1. dv is 2u du. So it'll be half log of u squared plus 1 plus arctangent u plus c. Okay, let's double check. If we differentiate this, do we get back that? It'll be half times 1 over u squared plus 1 times 2u. That 2 from the chain rule, and this half would cancel, and we still have a u on top. So yes, that's right. Okay, so we have this. Let's back substitute. Half log of x minus 2 squared plus 1 plus arctan x minus 2 plus c, and that's my answer. Okay. Hopefully this was helpful. Please like this video if it was, and please subscribe also if you haven't already. I apologize for the noise if you can hear it in the background. And yeah, please look out for the next video where I'll be doing another few problems. See you in that video. Bye.